Compared to Cranial Nerve I, Cranial Nerve II is a killer. Long before neuroscience even existed as a concept, Hippocrates had already linked visual loss to disease of the brain, not just the eye. That idea alone was quite radical for its time, but almost 500 years later, it was Galen who dissected animal eyes and physically traced the optic nerve back to the brain. And honestly, that was revolutionary. But it also introduced a mistake so influential that it dominated medicine for over 1,000 years. He believed that vision worked through visual spirits flowing out of the eye into the world. That single assumption shaped how doctors understood vision for centuries. Everything began to change in the 11th century when Ibn al-Haytham, often called the father of modern optics, proved something completely different. Light enters the eye. Vision is passive, not active, and the brain must interpret incoming signals. And it was quite a radical idea back in his time, so that people immediately accept a theory that shattered centuries of medical dogma? Of course not. Shifting scientific paradigms takes time, but this was the first experimentally proven framework to dismantle ancient visual theory and compel medicine to value evidence over authority. Over 500 years later, the journey continued with Johannes Kepler. Yes, that Kepler, who showed that images are inverted on the retina. So how did Kepler prove that? So this is the eye. And here we have the cornea on the outside, the lens inside the eye, the retina at the back, and let's say that we have an object, an apple here. Light travels in straight lines. Now, all light entering the eye must pass through a small optical system, which in this case is the cornea and the lens together. Light coming from the top of the object can only reach the bottom of the image plane, because it must pass through the center of the lens, and the light coming from the bottom of the object can only reach the top of the image plane for the same reason. So once rays cross, spatial orientation must flip. The image is upside down because rays from the top and bottom must cross at the lens, and crossing flips orientation. For the first time, vision became an actual equation. Retina, optic nerve, brain interpretation. It took over 1500 years to realize that the eyes are not windows of the soul, but rather biological cameras directly connected to the brain. But even after this breakthrough, something in this equation was still missing. Now, once anatomy and function were finally understood, another crucial realization followed. Cranial Nerve II is not a true peripheral nerve. It's an outgrowth of the brain itself, covered by protective layers called meninges, the same membranes that surround the brain and spinal cord, and supported by specialized cells known as oligodendrocytes, cells that help insulate nerve fibers in the central nervous system. These insights became foundational for clinical neurology, even though neurology wouldn't be formally recognized as a separate medical field until the late 19th century. So, what makes Cranial Nerve II truly special? Vision is unique because it's split and recombined. The retina is not a single uniform sheet, it's an active piece of brain tissue. Its job is to convert light into electrical signals, a process called phototransduction. Light first passes through multiple layers that you can see of retinal neurons before it ever reaches the photoreceptors. Rods and cones then translate photons into changes in membrane potential. That signal is already processed, filtered, and refined inside the retina before it ever leaves the eye through the optic nerve. To really understand vision, we have to divide retina into two halves, and this is where things start to get interesting. So the brain does not organize vision by eyes, it organizes vision by visual fields. So if we have two eyes, we can divide these visual fields onto left visual field and the right visual field. And more importantly, both eyes see both visual fields. This is why closing one eye does not remove half of your world. But the other important thing is that when the light enters the eye, the image on the retina, so at the back of your both eyes here, is inverted and reversed. So the left visual field falls on the right half of each retina, and the right visual field falls on the left half of each retina. Obviously, if we kept saying left and right retina, it would be quite confusing. So we can divide retina onto two halves, and the division is called hemi. So now we have hemi-retina. Hemi means half. And instead of using left hemi-retina, right hemi-retina, we say nasal hemi-retina. So nasal means closer to the nose. So closer here is nose, let's say, and we have nasal hemi-retina. And we've got temporal hemi-retina, so the half closer to the temple. And temporal here just means temple of the head, so it's not related to any time. So we've got temporal and temporal. Now, it's very important because, right now we've got the light from the left visual field and from the right visual field. And it obviously goes through the optic nerve, but it also reaches the optic chiasm. Here we've got optic chiasm. Alright, and now it's quite important because the fibers from the nasal hemiretina cross the optic chiasm, and the fibers from the temporal hemiretina do not cross it. And that's the rule. So we can say that the right eye, so the temporal hemiretina, stays on the right, and the left eye, so nasal hemiretina, crosses. And both signals end up in the right hemisphere. And in the right visual field, we've got left eye, so the temporal hemiretina stays on the left, and the right eye, so nasal hemiretina, crosses. So let's explain. So in this one, these signals then are then processed by the brain, by the visual cortex. And this arrangement is quite, I think, important because it preserves accurate spatial mapping. It allows binocular vision, and it protects vision. Because when some parts are damaged, I'm not talking about this part, so I'm not talking about the optic nerves. I'm actually talking about the optic chiasm or the visual cortex. If these parts are damaged to some extent, you can still preserve the vision. All of this anatomical complexity has huge clinical importance. Damage to the optic chiasm does not necessarily cause total blindness. Instead, it produces specific and predictable visual field defects. From an evolutionary perspective, the optic chiasm preserves accurate visual mapping between the eyes and the brain, and as a consequence of that beautiful architecture, vision is often preserved even when things go wrong. And this is very important because unlike cranial nerve 1, the optic nerve cannot regenerate. Losing vision can be devastating. so preserving even part of it can change a life. But what fascinates me the most is that despite all of this progress, there is still a final gap. We understand how light enters the eye. We understand how it's converted into electrical signals. We can trace those signals all the way to the visual cortex located at the back of our brains. But at some point, electrical activity becomes experience. Photons become color. Signals become depth, movement, and meaning. We know where vision travels, but we still do not fully understand how the brain turns information into what we actually see. And maybe it's one of the reasons why the brain fascinates me so much. Anyway, if you have any questions, you can email me using this email down below. And as always, stay tuned and see you next time.